So we will introduce today energy efficient strategies for construction of buildings. To start with, of course, when we talk about energy efficient strategies, we can consider that one of the main possibilities is to use renewable energy. Plus, we have several passive techniques related to building construction, as we discussed last time, building material, type of envelope, type of glass, etc. So the passive building strategies will include passive solar heating. So we'll see several options for use of solar energy. What are the main criteria for solar design? What are the solar strategies that can be adopted? In addition to also active solar technologies. When we talk about active solar technologies, this means that we need to use, let's say, an equipment that require power, like a pump, for example, but still the power consumption will be relatively very small compared to the consumption using fossil fuels or electricity. We know already that solar energy is a free source, so it has a lot of benefits. For both new and retrofit projects, solar energy can substantially enhance building design. Solar energy offers several advantages over conventional energy. First, it's free. We know that once we install the system, we can use the solar energy in a free way. But as we mentioned already, the main disadvantage is with the initial investment. And in next chapter, where we'll study the financial analysis and economical analysis, we'll see that this is the most important aspect that we should overcome in renewable energy. This is why we try a lot to do technological advancement in order to reduce the cost of implementation of renewable energy, because this is until now this is one of the main obstacles for development and use of renewable energy. So we'll try to, as much as possible, to reduce the payback period in order to have a renewable energy project that is economically viable. An additional benefit of solar energy is that it's available everywhere and it's clean, so it will reduce the demand for fossil fuels. And in addition, it can be used in parallel with other techniques as wind energy. And let's say sometimes we use a backup generator with it in case it's not sufficient. In addition, it can be building integrated, which can reduce the energy distribution needs. Now, whenever we consider solar energy, we know that this effect is by first radiation. So the sun will emit energy as electromagnetic radiation. And as we mentioned before, we have this radiation can be divided into three parts. So whenever you have the radiation flux hitting a certain surface, it will be divided into an absorbed proportion. So this is the total, let's say, irradiation from the sun. We have a part that will be reflected. And of course, as we discussed last time, it depends on the location of the window. So for windows that are exposed to sun during mainly summer, we try to increase rho. So in the design, we try to select a high reflectivity in order to reduce the proportion that will enter the glazing. So we have then the absorptivity, and this absorbed part will be, as mentioned, absorbed in the material. And we have a part that will be transmitted to the inner space. Okay.
Professor?
في chicken.
فيش كارمن قصص هذا الصح جابه وبيت بعد الدور يعني
انت ما كان فيكم دقوا قبل دقيقتين بس تماكم قعدت ساعة بعمل تشيكن وما طلعوا طيبين.
Guys, do you hear me?
Yes, doctor, we weren't. Now we can hear you.
Now you can
Now,
hear
yeah.
me? بس آخر شيء شو كنا عم نقول؟ بس وقف الصوت.
About
chicken.
increasing grow in the summertime.
great. يعني مش okay. Great. يعني هذا ما قطش كتير. Okay. So the solar energy is really very high, and if we can benefit to the maximum from it, we can reduce a lot relying on fossil fuel consumption, because the solar energy is equivalent to the energy of a 5,725 degrees furnace. So imagine the high temperature provided, and it's 36,000 times the amount of energy currently provided by the total world oil consumption per year. But the issue is that we are not able to benefit completely from it. So this is why we are trying to increase the number of technologies that can use solar energy, because if we use it appropriately, we can save a lot of money. Now, the amount of energy that reaches the Earth's upper atmosphere is about 1,350 watt per meter square, which is the solar constant. Now, of course, depending on the countries, this solar constant will vary because, depending on the sky condition. For example, in Canada, the peak solar intensity varies from 900 watt to 1,050 watt per meter square. The peak solar intensity is at solar noon when the sun is due south. And all of these issues should be taken into consideration whenever, let's say, you want to study retrofitting a building, or when you want to study heating and ventilation configuration for new buildings. You should implement the weather data. And of course, for each country, you have statistical studies to give us the weather data that can be implemented to the energy software in order to compute the variation of the heat amount that will enter the space depending on the season. Now, sun is the source of all energy available on Earth, directly or indirectly, including fossil fuels, because the formation of fossil fuels requires high pressure and temperature. And the high temperature will be here because of the sun. So the sun will affect all types of energies, including biomass, nuclear energy, fossil fuel, all systems using directly solar energy as solar panels, photovoltaic, etc. So it can be used directly or indirectly, depending on the type of energy we are talking about. Now, energy from the sun reaches the Earth as direct, reflected, and diffuse radiation, as we mentioned before. Direct radiation is highest on a surface perpendicular to the sun rays. This is why, if you want, for example, to design a PV system, you should optimize the orientation of your PV cells. And we should study, if you want, the sun direction in order to decide what is the best orientation to use for this system. On the other hand, for diffuse radiation, it is the energy from the sun that is scattered within the atmosphere by clouds, dust, or pollution, and becomes non-directional. For example, on a cloudy day, 100% of the energy may be diffuse radiation, but on a sunny day, it can be less than 20%. In general, the majority of devices work on direct radiation, but if we can use also diffuse radiation, we can benefit more than from the solar energy. The amount of the sun's energy reaching the surface on the Earth will also depend on the cloud cover, air pollution, and location, and the time of the year. This is why, as we mentioned before, all of this data can be implemented as a weather file that will be an input to the software, energy software. So if you use Energy Plus, or if you use Hub, or if you use any software for HVAC, you should provide the weather data. And in majority of these softwares, we have the weather data for each country built in within the software. Now, when we talk about the design of a solar system, we need to tackle three aspects: collection, storage, and distribution. A passive solar building consists of, whenever we say it's a passive solar building, so all, if you want, equipment used to collect, store, and distribute solar energy should be passive. When we say passive, so we don't need any external power to supply. And we don't have pumps. You should not have pumps or fans, because these devices will use electricity. Of course, we know that using pumps might enhance the efficiency, because You can control the circulation, let's say, of water. So this is why sometimes we justify using active solar systems, because it's true that we need to supply electric power to use them, but they will allow us to use the solar energy in a much more efficient way. So when we talk about a passive solar building, so we'll just consider natural energy flows. And for example, you can create air motion by buoyancy effects. So as we discussed also last time, Trombe wall, for example, will act based on this. So we just rely on heating air. When you heat air, it will move upward due to creation of density difference. And then you can create circulation of air within your space. We can talk also about using like thermal mass. We discussed also that thermal mass can reduce fluctuations of temperature within a space. So you have to put a thermal mass with high thermal capacity, or you can use phase change material also embedded within the wall, etc. And they will just work on the concept of heat transfer by radiation, conduction, and natural convection without the need of implementing any extra equipment. And windows will work as collectors, and interior materials will be the heat storage medium. So in this case, you need just to ensure windows of high transmissivity to collect the solar energy. You can store it within your building by the thermal mass that you can put under the floor, you can put in the walls, etc. And to distribute it, so whenever you need, whenever you have high temperature within the space, you store it, and when needed you can get it back. If you are using thermal system, it will deliver it back when the temperature in your room will fall down. And sometimes also we'll see that let's say you can control, for example, the natural ventilation. So let's say whenever you have let's say decrease in temperature, okay, you can control the opening and close of vents in order to increase it in winter or reduce it in summer. Now, an active solar system will use mechanical equipment to collect, store, and distribute the sun's heat. Active systems will consist of solar collectors, a storage medium, and a distribution system. And in general, whenever we talk about, let's say, distribution systems, they will involve pumps that will use electrical power to ensure appropriate distribution. So active solar systems are commonly used for water heating, space conditioning, production of electricity, and process of heat. And also, in general, we can use hybrid systems, which will combine two or more energy systems or fuels. Hybrid systems are widely used because they will combine advantages of several systems, and they can constitute a backup. So let's say when you combine, for example, solar and wind energy, when you don't have solar energy, you can rely on wind, and when you don't have wind, you can rely on solar energy. And if not enough, you can have a backup as a generator, and you can combine them with an active system. Now, of course, the key aspects of passive solar design are interlinked depending on the design parameters that we are considering. So first, we should determine the optimal location and orientation of a building. So if you construct from zero a building, you can, as we mentioned, for example, you can use Energy Plus to study several orientation in order to optimize the reduction of energy consumption. You can also rely on fenestration area because it will help you to create shading for your building and to reduce, let's say, the cooling load. You can also use in appropriate location thermal massing and optimize the envelope characteristics. So as we mentioned, we can combine several layers of different conductivity together in order to create the optimal insulation needed. Even not all the walls will have the same characteristics, as we discussed last time in the Energy Plus software. The amount of insulation then should be determined. What is the amount needed? And always, we should remember to have a compromise between the cost and the design, because we might have a very good design in reduction of energy consumption, but if we study the cost, we will pay much more than we will save, then we'll not go through this. So we try to do a compromise between the complexity and the efficiency. We can also, of course, use also as passive techniques shading devices. So we can determine which zones we should in which zones we should use shading. And sometimes, you know, of course, that you can have on and off. So you use devices where you can put shading when you want and remove it when it's not needed. Now, concerning the effective thermal storage, we can put thermal storage at locations that are exposed to sun, and we have possibility of overheating. So these are the zones where we put thermal storage, and then the energy will be delivered when needed. For example, we can consider, if we talk about sensible heating, we can consider the concrete, which is used in the building envelope, and it is characterized by a high thermal capacity, so it can store energy in sensible way. Because why we say in sensible way? Because the temperature will increase, but the amount of increase is really small, because we know that Q sensible is equal to MCP delta T. Okay, and since MC is very large, so even for a certain amount of energy stored, even if you have increase in temperatures, this increase will be limited, because since MC is very large, delta T can be neglected. So it's still a sensible load, but without high increase in temperature. And also, on the other hand, also we can use latent energy. This is associated with phase change material. So in this case, the temperature will remain constant. We don't have any increase until a complete change of phase, let's say from solid to liquid. Now, what are the different steps of design? So as we already seen, we have several steps of design. We can apply them to the design of solar systems. So we should first set the performance targets for energy sources and uses. So what is our final goal? What is the amount? If you remember last time, we set a certain level to reach to consider a building passive. So we should reduce the energy consumption to a certain extent. So we say this is our goal. We need to reach these numbers. We don't want to exceed this level of heating and cooling needs. And then we try to study several strategies until reaching this goal. So we should minimize heating and cooling loads through orientation, massing, envelope, and landscape design. We should maximize solar and other renewable energy use to meet the building load, then to design efficient HVAC systems. So we can study, you can here use, for example, if you know PVsyst, if you have taken a solar energy course, you can use the software PVsyst, okay, which will help you into designing a solar system, okay, in an optimal way for your building. So we can then design efficient HVAC systems that are integrated with the building envelope performance characteristic. And we can use simple energy simulation tools and detailed simulation in evaluating options that at the early design stages, and later to assess alternatives. So if we are comparing several alternatives, we need to use simulations, as we mentioned before, in order to be able to select the best one. And of course, before this, we can do a decision matrix that will help us to reduce the number of alternatives. And then when we are done with, at the final stage, we are comparing just 2 to 3 alternatives, we can go into detail, doing simulations and doing detailed economical analysis in order to select the best option. Now, as we discussed, whenever we want to design the windows, we should appropriately select the U value desired, okay? And you already know that in majority of buildings, whenever they are talking about good characteristics, they say we are using double glazing for windows. So here we have a comparison between simple glazing clear, double glazing clear, and double glazing with low emissivity. So first, we can see that with the simple glazing clear, the percentage that is transmitted is very high. So we have 84% that will be transmitted to the inner space. While in case of double glazing clear, it is reduced by 14%, so only 70% will enter the space. And for double glazing with low emissivity, we can go down to 62%. And concerning what is the solar heat gain coefficient? The solar heat gain coefficient, if you want, is the total amount that will enter the space, because we have first the transmitted part, okay, but also whenever we consider, we have the reflected part, and for the absorbed part, it will be after divided into two parts, one that can get out, so let's say by convection to the outer side, and a part can go in by convection to the inner side. So we can find the total solar heat gain coefficient as the summation of the parts that will come in. So for the simple glazing, we have 86%. For the double glazing clear is 76%. And finally, for the double glazing with low emissivity, it's 72%. So we can see that for double glazing, we have the lowest amount that will enter the space. Of course, in some locations, maybe where you want to have a high transmission, you can allow for single glazing. But in majority of locations, we prefer to have the double glazing option to avoid any overheating of the space.
Professor?
Yes.
In the previous image, what's the K value?
K is the conductivity. Okay, you know that the conductivity value, whenever you want to increase the resistance to heat flux, you should reduce the conductivity of the material you are using. Okay, because whenever you have a wall or any surface, and you have heat that can go through it, it can go through it by the conduction process. So if you want to limit the value of the heat that will enter the space, you should have a material with high insulation property and low conductivity. Okay.
Yes, and for the absorbed part that goes to the space.
Yes.
Is it by conduction or convection or both?
Mainly, it is by conduction within the element, and by convection to the space. And if you want,
yes.
At the end, whenever you want to study the overall insulation, okay, you should consider first. You start from what we call T infinity, which is the temperature outside. Okay, so you have T infinity 1, which is the temperature outside of your building, and you have T infinity 2, the temperature inside. Okay, and if you want to study the overall resistance, you will start from T infinity 1. Okay, you say that first you have a first resistance to heat flux towards your space, which is the convection from the outer side. So you have what we call 1 over HA. 1 over HA is the resistance to convection. Okay, then when you enter your glazing, you can have, for a simple one, let's say you have one layer of glazing. So you just have the resistance to conduction. The resistance to conduction is given by the length, the thickness of your glazing over Ka, the conductivity times the area. And then you have, at the third stage, you have the convection with the inner space. Okay, so if you want to find the total, if you want U value, the U value is related to the total resistance from T infinity 1 to T infinity 2. Okay, so you have here Hn times A. So if you want to compute the total resistance to your flux, you can say that total resistance to heat transfer from the outer to the inner side is equal to summation of these three resistances: convection, conduction, convection outside, conduction, and convection inside. Okay, and the U value that you use a lot in energy softwares can be computed as 1 over U overall. Okay, for the overall, you can count from the external to the inner side times A. In general, in energy softwares, you enter the overall U value after taking into consideration convection, conduction, and convection. Or whenever you specify the material of your envelope for the software, it will, it's built in. This calculation will be built in within your software. It will calculate the overall U value in order to compute what is the resistance to heat flux from the outer to the inner side. Okay. Any other question? So here K, I should mention what it is. In general, K is for conductivity, but it can also be the overall U value. Okay, so you can know from here. Okay, here they said coefficient K is in watt per meter square Kelvin. So it can be, it is the overall coefficient value. Okay, because the overall coefficient value will have this unit. Because you know that heat transfer K in total, Q, is equal to UA delta T. Overall, this is called the overall transfer coefficient that will take into consideration all of resistances, convection and conduction, times delta T. So since we have the flux in watt, okay, the area in meter square, and delta T in Kelvin, so you will be in watt per meter square Kelvin, and it will take into consideration the conduction and convection resistance. Okay. This is why you can see here the highest U value, lower is U, higher is the resistance. This is why here you have the lower value of K for the double glazing with low emissivity. An intermediate value is for double glazing clear, and the highest value of K is for simple glazing clear. Because higher U means lower resistance. It's inversely proportional with the resistance to heat flux. Now, also when you want to design your windows, okay, you can play with the size. So you can optimize the size of windows in order to enhance the performance of your building. So if you are, of course, if you are retrofitting a building, you cannot play a lot with this. But if you are building if you are considering the design of a new building, you can play with the window size, and you can study the optimal size of the windows in order to have the best. Now, dear students, do you hear me now?
Yes.
Dear students? Okay. Yeah, sorry. So we were talking about window sizing, Mahek, when we had a code. Okay.
The slide before.
Oh, okay. Okay, so we were done with the U value. So as we have seen, the overall heat transfer coefficient U will be low when we have a high resistance to flow, which is required when we, in general, when we design a building, we prefer to have low U values in order to enhance the insulation properties of our glazing. Except in positions where we want the energy of the sun to come in high amounts. But as you can see, 86% is really high. So even the double glazing with low emissivity will allow for a heat transfer towards the environment, the indoor environment, but we can control then this in a better way to avoid overheating of the space. Now, concerning the design of windows, so we know that, especially if you are designing a building from zero and not retrofitting a building, because if you retrofit a building, it's not easy to have a new window size. We should then have major changes in the architecture of the building. This is why, in general, we play with window sizing for construction of new buildings, and then we can optimize the total size of window in order to enhance. If you want to have an optimal energy transfer to the space, so we can study what is the percentage of the total area of the south facing that should be of window type. Concerning the window orientation, the greatest amount of energy received through a window is when the sun is perpendicular to the window and 30 to 35 degrees above the horizon. And here we'll see that this recommendation will allow us to have a design that of shading that can play a positive role in winter and summer, as we'll see in next slides. Now, concerning the east and west facades, we know that they receive maximum solar gain in the summer. So this is why a south-facing surface will receive its annual maximum in the late fall or winter. This is why we recommend to concentrate windows at south-facing, because we desire to receive a high amount of energy during fall and winter, while during summer we want to avoid this. So this is why we try to reduce putting high areas of windows on east and west facades. So here, this is what we were talking about, okay? We can see here that shading can be designed in a way that it will allow the sun energy to come in during winter and it will block it during summer. Because if we study the orientation of energy rays, okay, we can see, for example, that during summer we have a certain inclination that is different from the inclination during winter. And that's why we can design appropriate shading with a certain inclination that will block the sun rays during summer, and it will allow these rays to enter during winter. So this is a very simple passive strategy that will optimize the use of solar energy. It will block it during summer, and it will benefit from it during winter. Now, we can also have movable shading, okay? So we can not only use external shading, but also we can use internal ones. So for example here, if we consider, let's say, in the following figure, okay, whenever we have a high temperature within the space, okay, we can put our these shadings that are removable, and they will block the penetration of sun rays during the summer, while in case we want to benefit from solar energy during the winter, we can rely on convective effects. So what we can do here, we just have a space between the window, okay, and this shading, and we have operable here vents that we can close and open depending on the season. So for example, during summer, we can close this. We can close the vents here, so the energy of the sun will be blocked. While during winter, we can have these openings, and then whenever the sun energy will hit the glazing, it will warm air in this space, and it will allow it to circulate by natural convection, because once heated, the density will be reduced and it will move upward. So we can allow here heat transfer by convection, plus also by radiation from the hotted surface to the inner space. Now, concerning thermal mass, we have several strategies to use thermal mass. Two major options for thermal mass placement is in passive solar design are the direct gain and trombe wall or collector storage wall. So when we talk about the direct gain, so this is by using glazing windows, okay? And so we can benefit directly from the energy of the sun by radiation. And when we talk about trombe wall, we can create natural convection, because by opening the vents when needed, we can create circulation of air, as we mentioned before, by natural convection. And another type is the collector storage wall. So as we mentioned before, we can use thermal mass, or we can use PCM materials embedded to the thermal envelope in order to play the role of storage of energy when we have excess of energy, and release of energy when needed during the night. So here, for example, we can see how thermal mass can produce a very positive effect. So if we compare a heavy mass building with a light mass building, so a heavy mass building will be characterized by an envelope having a high thermal capacity, while a light mass building is characterized by an envelope with lower thermal capacity. So we can see that for the light mass building, during the day, the sun rays will be able to cause overheating of the space, while during the night will have a high decrease in temperature, creating a cooling sensation. On the other hand, if we compare the same for the same weather, so during the day, what will happen is that the thermal mass will absorb the excess of energy, so it will regulate the temperature to a comfortable temperature. And during the night, when the temperature will drop in normal cases, the thermal mass will release back the energy stored, so it will allow us to maintain a nearly uniform temperature between the day and night, so it will reduce a lot of the fluctuations that are observed here in normal scenario. You can see here a high difference between the day and the night, overheating during the day and relatively cool space during the night, while here the difference between the two temperatures is much smaller. Now we can see that sometimes the thermal mass will not be enough to create thermal comfort in all times, but at least it can reduce a lot the need of HVAC system for a high number of hours. So here, for example, we can observe the variation in temperature within a space having a certain thermal mass. So we can see that, for example, from 10 a.m. to 5 p.m., we have the sun, so it will play a role of storage. Then from 5 p.m. to 11 p.m., the energy